The harmonic oscillator and the rigid rotor provide very good basic models for the rotation and vibration of diatomic molecules. But another area where they can be used, those two models, to mimic something that actually happens in real molecules, is they can be used to display a little bit of the effects of rotation-vibration interactions. Now, what do I mean by that? Okay, imagine that you have a molecule that's rotating. Okay, and we've drawn this before as some sort of rigid rotor rotating about its center of mass. But now, if that molecule is also vibrating, it turns out that those two motions can interact with one another. Now, what does that mean, really? Well, one of the ways you can think of this is that as this molecule is rotating, it exerts centrifugal force that pulls the atoms apart. So in other words, it's actually supplementing, if you will, some of the motion that would normally happen due to the normal harmonic oscillator oscillation of the two masses relative to one another. All right, it's also true that as this thing is oscillating, it's modulating the moment of inertia of the molecule so that it's changing that, and that also has an effect on the rotational energy levels. So the net effect is that we have vibration-rotation interactions that are going to modify those energy levels. And in modifying those energy levels, it means that we're going to be able to observe this when we do the spectra. Now, the most basic way to depict this interaction is that the Hooke's law force constant, that is a restoring force for the harmonic oscillator, all right, basically looks like this. The Hooke's law restoring force is going to be the force constant times the difference, the displacement of the oscillator relative to its equilibrium position, which I'll call R sub E. All right, at the same time, there is this centrifugal force, which we can depict as the angular momentum squared divided by basically the moment of inertia of the molecule. And when these two things balance, as are shown here, where we have a, I think this is actually supposed to be Re cubed, where we have a force that forces the molecules apart and another force that forces the molecules together. They need to balance, if you will, when these two forces are acting on a rotating and vibrating molecule. All right, so what does this mean? I'm not going to go through the math of this. That's actually available in the Macquarie reserved reading book if you want to take a look at it. But what I am going to do is tell you what the result is from following through the logical conclusion of the balance of these two forces with one another. All right, and it looks something like this. All right, when we carry through all the mathematics to write down the total energy for this system, what we would end up for the rotational part, so I'm going to write this as E sub j, and it's going to be evaluated at the equilibrium bond length. It will look something like this. We'll have a first term, which is the one that we're used to seeing, which is simply the expression of the energy levels of the rigid rotor. And that's going to be this term times j plus 1. But we'll also have another term that's now coming about because this is no longer a rigid rotor, it's now a vibrating or a non-rigid rotor. And that second term is going to look like this. It'll be h bar to the fourth divided by 2k, where k is this restoring force from Hooke's law, times mu squared re to the sixth. All right, so that's the constant that goes before this next term, which is in fact the square of the j dependence in the first term. All right, so this now becomes an expression for the rotational energy levels of this system when it is able to vibrate with a force constant of k. Now, I should mention that there are higher order terms that we are not including here, but they're necessarily much smaller than these terms, so this is going to capture most of the effect that we would see. Now, what we want to do is we want to recast this in the following way. We want to write our E sub j as, and I'll say this will be 1 over hc E sub j. We want to write this as a rotational constant times j plus 1. So this is just what we've had before. And we also want to include this second term, I'm going to use a second constant with a tilde over it, which will be times j squared, j plus 1 squared. This second constant, d, is something that we'll have a special name for. We'll call it the centrifugal distortion constant. And it is basically a way of measuring the effect of centrifugal distortion on these energy levels. Now, this is a positive number, okay, so which means that this energy correction is going to squeeze the energy levels closer together. So this is the centrifugal distortion term. And one may ask, does it make sense that it's squeezing the energy levels closer together? Well, the vibration of the molecule, the fact that the molecule is not rigid, means that the rotational motion is going to cause the two atoms to drift a little bit farther apart. So they're going to want to assume a longer distance. And in fact, that longer distance would be if we solve for this r in this equation. All right, that longer distance, though, reduces the moment of inertia for the molecule, and since that's in the denominator of this equation for the energy levels, it means the energy levels are going to get closer together. So this is how they get closer together, and I'll simply remind you that these are the rigid rotor levels right here. So this would be what we would have if there were no centrifugal distortion. When we add the centrifugal distortion, we'll have this additional thing going on here. Now these two constants, we've already seen B, but I'll remind you that this B tilde is just 1 over hc times the thing that we had in front there, which was h bar squared over 2 mu re squared. And so if I cancel out the factor of h, and I'll still have a factor of 2 pi because this h bar is h over 2 pi. So I'll have a 2 pi that comes down. I'll have h bar remaining in the numerator, 4 pi c mu r0 squared. Now we saw this one before in the rigid rotor spectra, and we used this formula to solve for the equilibrium bond length. I'll make that an E now. And in terms of the rotational constant B. So this is an old equation for us, and this tells us what B is in units of inverse centimeters. We'll have a similar thing when we do the D tilde. It's basically going to be this constant up here divided by HC. So if I do that, and I'll spare you the details of going through each step, but it's going, the h in the denominator is going to cancel one of the h's up here in the numerator, so I'll end up with an h bar cubed. I'll bring a 2 pi down. That was part of the h bar that we canceled. We'll have the factor of c, and now we'll have k mu squared re to the 6th. Okay, so this will end up being our expression for this centrifugal distortion constant, and I'll note that it too is going to be in units of inverse centimeters. All right, so now we have expressions for each of these constants. What does this mean? Well, it means if we see a spectrum, and in effect what's going to happen is instead of having those adjacent lines in the spectrum spaced by a constant amount, they're actually going to get closer together as we go higher because of this centrifugal distortion. So we can actually measure accurately the positions of all of these lines and use that with this equation here to solve for these two constants. All right, just as an example. So we still have these selection rules, delta E j to j plus 1. We would write something like this. And it would be comprised of the following. We'd have our B tilde constant. And when we go from j to j plus 1, we'll have j plus 1 times j plus 2 minus j times j plus 1. Okay, and that was the transition that we had ordinarily with just the rigid rotor. But then we'll also have this term that comes from centrifugal distortion. And it will be proportional to the following. We'll have j plus 1 squared times j plus 2 squared minus j squared times j plus 1 squared. So all I've done is plug in j and j plus 1 into this equation up here and subtract one from the other. All right, now this stuff, once again, I'm going to have a factor of j plus 1 that I can factor out of that. I'll have j plus 2 minus j, which just gives me a factor of 2. So I'll put the 2 out in front, and we've got the first term. And it's the same, of course, as the term that we got before. What about this side? Well, I have minus d. I'll have a factor of j plus 1 squared that I can factor out. But then I'll also have a j plus 2 squared minus j squared. Well, j plus 2 squared, if we expand it out, is going to be j squared plus 4j plus 4 minus j squared. So these two will cancel. I'll end up with 4j plus 4, or 4 times j plus 1. Okay, well that j plus 1 I can combine with that. So my final result for this energy difference is going to be 2b tilde times j plus 1 minus 4d tilde times j plus 1 cubed. So this is what we would find for the for the transition energy between two rotational levels when we include centrifugal distortion. Now I'll mention that you can separately show by using the fact that our harmonic force constant is equal to mu omega squared, or in fact this is equal to 4 pi mu nu squared. We can use this definition in our definition for d up here to actually rewrite d as follows. We can write that as 4b cubed divided by this harmonic frequency squared. So what this means is that if we use a spectrum, we can use the spectrum to find values for b, we can find a value for d, and once we have both of these values, look at this. We've got d and b here. Oh, and that should be a cubed. I apologize. 4b cubed. What's left to find is this. So not only can we learn about the moment of inertia and the equilibrium bond length from these factors, but we can also use them to tell us what is the harmonic frequency of the oscillator. All right, so all of that can be embedded in the spacing of these lines in a rotational spectrum that's part of a row vibrational spectrum when we have centrifugal distortion. So really a fascinating amount of information that you can get from these spectra if you know how to look and how to analyze.